Okay, good morning, everyone. Welcome to the keynote session on legged locomotion. My name is Katja Mombauer. I'm from the Karlsruhe Institute of Technology. I'm professor in robotics there, and it's my pleasure to chair this session. So legged locomotion is a very important topic in robotics because it allows robots to go in very difficult terrains and to explore a lot of unknown environments. Legged locomotion also is a very challenging topic because robots have to maintain stability, they have to find good footholds, and so on. And it's also a very timely topic because we have all these new platforms coming up, all these great quadruped and humanoid robots that all have to be taught to perform legged locomotion in new, challenging, unknown terrains, which also dynamically change over time. So in order to perform legged locomotion, you need good hardware, but you also need good software, you need good algorithms. And there's a lot of research going on finding good algorithms that allow robots to adapt their locomotion to new situations, to interact with humans, and to also do that in really unknown situations. So in that session today, we have a set of four great keynote speakers that look at legged locomotion in very different situations. So, we are starting with Sarah Bergbreiter, who I would now like to ask to already set up, and she will take us to the area of micro robots and look at locomotion in that area.
Great. Thank you so much, Katja, and thank you in the back for working on the technical difficulties. So I want to talk a little bit today about locomotion at small scales. Locomotion is fascinating. Like, the idea of a robot successfully moving from point A to point B is probably the reason I got interested in robotics in the first place. And even at big scales, this is incredibly challenging. And I'll focus on legged locomotion in this talk, like the ants that you see in this video, but these small locomotors, like the ants and small robots that use legged locomotion, ultimately have a lot of challenges that are perhaps enhanced at these small scales. So they have challenges around energy, right? Can they carry enough energy with them or actually scavenge energy from their environment to actually be able to complete useful tasks? They have challenges around computation and control. Can they kind of navigate the terrains that Katja was just talking about, even when they're really small? And they just have challenges around size. Like, these robots are often smaller than the sensors that people put on their bigger robots. And everything around them looks incredibly large. So why even bother studying locomotion at small scales? Well, in addition to designing robots that can ultimately get into smaller spaces, the vast majority of legged locomotors in biology are actually small. And I think there are some really interesting lessons, I think, that we can take from these locomotors that ultimately translate to robots across scales. So how can we design our robots to actually help solve these big challenges at these really small scales? I think robotics has traditionally used two main design spaces to do that, kind of control as well as geometry. And on one end of the spectrum, we have things like Atlas that use a lot of computational control, a lot of actuators to ultimately get really effective locomotion. At the other end of the scale, using geometry and leveraging passive dynamics actually allow us to get really efficient locomotion, like the Cornell passive dynamic walkers. And I'll argue that we also have a third design space that we can leverage in materials. So the soft robotics community over the last 15 years or so has really showed that different material choices can ultimately help in improving locomotion at various scales as well. And in this case, I want to, in this talk, show how we're leveraging all three of these design spaces to ultimately improve locomotion when you're really small. And by small, I typically mean kind of gram scale and below. So I'm going to start with the material side. And the question is how different material choices of our legs can ultimately help control locomotion at small sizes. So we can think of the slip model. Many of you are probably familiar with this, the idea of a mass on a springy leg. And no matter kind of how many legs you have, you can kind of collapse it to this slip model. And if I think of a material choice, like a polymer choice for my leg, that polymer will provide both compliance, right, the springiness in the slip model, but it also provides, for polymers in particular, viscoelasticity and damping in that leg. And one of our questions with this research was really trying to understand how these different kind of compliance and damping parameters ultimately affect locomotion, especially at these small sizes, in this case, kind of gram scale robots. And this is work from Ryan St. Pierre, who is a PhD student now at the University of Buffalo, and our collaborator, Jonathan Clark at Florida State, and his student. And in addition to the modeling side of this work, we also created kind of physical models of this system using magnetic actuation. So these don't have power and control on board, but offer an effective platform to study locomotion with varying leg types. So we can change out the materials in these legs, and then they're actuated by an external magnetic field to provide torque at the hip. And so in this case, I'm showing results from 3 different material choices of the leg. So on the x-axis, we have the stride frequency for these systems, and on the y-axis, we have the forward velocity of these systems. So the black line was a really heavily damped, very viscoelastic polymer that we could 3D print that effectively acted like a rigid leg. And so that one didn't do so well. The red line shows a material that is on the stiffer side, but more resilient. So we would assume that this might actually lead to more efficient locomotion over time. And the blue line up there actually shows a slightly more damped material with a little bit less stiffness associated with it. And ultimately, we get our best locomotion, our most stable locomotion, when we have that right amount of damping in our system. And we can ultimately achieve locomotion speeds on the order of 12 body lengths per second, over 220 centimeters per second for this system. But my favorite part about this, perhaps, is that we can actually scale this over multiple orders of magnitude and mass and study the same questions from the gram scale all the way down to the milligram scale, as in the case of this kind of 1 milligram, 2.5 millimeter long robot. So this is truly the size of small ants at this point. And in this case, one of the interesting things we found is that the material choices of the legs still affect locomotion at these really small scales. And if you think back to the slip model, that's actually really surprising because we don't have the mass now to actually deform that leg in any fashion. And our hypothesis here is that the contact adhesion between the material and the ground is actually resulting in different performance for different materials in this case as well. And I think one of the interesting takeaways from this is that we can actually leverage physics at these smaller size scales that we would never think of leveraging in larger scale robots, like these kind of contact adhesion points. And we didn't just test this over flat terrain. One of the nice things about working on small scale robots is that you can literally take some aluminum foil, crumple it up, and now that is rough terrain for your robot in this case. And like the biological locomotors that inspired these small robots, they actually do really well, even with this very simple control, right? It's just effectively a 1 degree of freedom control on this robot. So switching gears to geometric design, this is Zippy, and this is a robot that we presented at this conference. This is a 3.5 approximately centimeter tall bipedal robot. So this only has 2 legs. It's about 25 grams. And in this case, Zippy has also kind of really simple computational resources. So it's much heavier, right? But it's got power and control on board than the robot I just showed, but it's still really simple in control. And in this case, we leverage the geometry of the feet is one of the really important parts of this. So this has a single motor, but the foot curvature here, the feet are curved in both the pitch direction and the roll direction, and that gives us the kind of passive dynamics that allows the clearance for the swing leg to kind of swing through and actually locomote in this case. And this is a collaboration with Aaron Johnson at CMU. And one of my favorite parts of this particular robotic system is that we actually get this kind of interesting emergent skipping gait at higher stride frequencies in this system. And this is probably a result of both the way that we control this robot. So servos don't scale well down to these small scales. So we actually use a hard stop to control the sweep angle of the leg. So I think it's a combination of that hard stop as well as how the inertia and the mass of the robot scale in comparison to how the torque from the motor ultimately scales down to these small scales. Right, but 25 centimeters per second for a robot of this size, its legs are only 2.5 centimeters long, giving it a relative velocity of about 10 leg lengths per second, which as far as we know is the fastest bipedal walker, large or small, out there. And I think if you had told me 10 years ago that a small biped would be able to handle rougher terrain at these tiny scales, I would probably not have believed you. I think we got some insight from the quadrupeds that I just showed you that stability may not be, we may get some benefits from scaling down in stability, but I certainly wouldn't have imagined that kind of robot leveraging passive dynamics would be as effective as this over varying terrain right here. And one of the things that I haven't mentioned yet is that Zippy actually lasts about an hour on its battery, which at 25 centimeters per second is approaching effectively almost a kilometer of travel, which using a single motor, we actually get some interesting benefits for efficiency at small scales as well. And so switching gears once again, I think there's some really interesting things that we can think about once we start kind of adding on to that single degree of freedom control. So Zippy and the small quadrupeds that I showed are really only single degree of freedom robots, but we can actually add multiple motors and more complex mechanisms to add interesting control features that we don't otherwise have access to at these small scales. And this robot here is Picotar. This is work from Sukjun Kim. And in this case, Picotar leverages a fabrication process in the lab in which we 3D print actuators and really complex mechanisms like this 5-bar leg directly onto flexible printed circuit boards. And the flexible printed circuit boards in this case don't necessarily have power and control on board right now for Picotar, but they enable us to kind of integrate that power and control for autonomy in the future. So each of these legs has 2 motors at the base, and by controlling the amplitude of actuation, they basically look like rotary servos, but they're electrostatic in nature. By controlling the amplitude and the phase between those 2 motors, we can get different leg motions, which can ultimately lead to different gaits in our robot. And so on the left here, you see a kind of typical tripod gait for a hexapod. On the right is a pronking gait. And that ultimately enables us to get reasonably high speeds with large step sizes, as well as the ability to switch gaits as we're locomoting and get over some more complex terrain. And of course, we can do interesting things like push little foam soccer balls into goals with this robot right here. So in general, the things we've been working on in the lab are locomotion at small scales. We leverage everything from jumping to wheels to the legs that I've presented in this talk. And I think really the interesting points here is that we can leverage material choices, geometry, and control to ultimately improve locomotion efficacy and efficiency, both at small scales, and I think there are lessons from this that we can ultimately take away for larger robots as well. And of course, this isn't possible without a lot of incredible students contributing to this and funding agencies supporting this work as well. Thank you very much.
Okay, thank you very much, Sarah, for these great insights into the world of tiny robots. We have a few minutes for questions. I would like to ask everyone who has a question to line up at the microphones. And I would also like to ask the next speaker already to come up here. Okay, are there no questions? Okay, so while you're still thinking about questions, I of course have one. So, so what would you say, like, how how important is the mechanical system, like the mechanical properties for small robots? Like, can we transfer one-to-one on the small? I mean, it's much harder to fabricate, but is the same true for small robots? Or like, as you had in the beginning, you had the passive dynamic robot.
Okay, so the question that is... Can you turn on the microphone again? The question... Oh, there's a question. Go to the podium. So the question was if you can actually leverage some of the mechanisms and the dynamics at these small scales. Absolutely. I think that's one of the things that we showed is leveraging both the material properties, which give us the dynamics, as well as some of the geometry and those passive properties as well. You can yell it.
Yeah, you can, but you should be on.
I have a very general question. Now, you didn't hear any of it. Okay. I was curious also, you have these sort of very simple, relatively simple, tiny robots, and I was curious how we can maybe leverage some of this insights for larger robots. You said you can, and I would love to know how. If
Yeah,
you have any thoughts.
I think some of these principles definitely scale, and we've already seen that in existing robots. So the idea of using very simple control, but interesting material properties, you've seen in robots like ICRA and Rex and those sort of things. They have a little bit more control than we do, but I think that those properties typically, we've seen that benefit larger robots as well. I think for the bipeds, one of the interesting things that we're looking at is that the small robot actually way outperforms the larger versions of those that we have. And one of the interesting questions is like, why? Like, is it just kind of the scaling laws and this kind of torque of the motor and the inertia of the legs, or is it something actually more that we can actually take those lessons back to the larger scales? Those are questions we're still trying to answer.
Okay.
Thank you.
Thank you very much.